Hello, everyone, and welcome to a fantastic talk titled Breaking the Monolithic ML Pipeline with a Feature Store. Our guest presenter for this talk is Jim Dowling. He's the CEO of Logical Works and an associate professor at the KTH Royal Institute of Technology in Sweden. He's the lead architect of the open source Hopsworks platform, a horizontally scalable data platform for machine learning that includes the industry's first feature store. I encourage you to visit their website at logicalclocks.com. They have an impressive product, and Jim will be around for the rest of the conference, so also please feel free to reach out to him afterwards. And without further ado, Jim, the screen is all yours.
Thanks, Juan. All right, I'm going to share my screen. You can write, questions in the chat. I'll probably get them towards the end, and maybe Juan will interrupt me. But feel free to write questions as we go. Here we go. All right. So I'm going to talk about feature stores, end-to-end machine learning pipelines, so MLOps, and what feature stores mean for these end-to-end machine learning pipelines. And we'll see that it's about breaking them up, really. And I'm going to start by motivating the feature store. And I'm going to motivate the feature store with a story. And I'm going to tell you this story. We're in MLOps world. I assume most people know what deep learning is. But the jellyfish here reminds me of deep learning, because the jellyfish, if you have very rich sensory input, you can have incredibly complex behavior in jellyfish. They can munch, they can move, they can mate. You can even stack them to make them more complex. You can see a nice stacked jellyfish here. So it's very similar to deep learning at that level. And also you'll see that the jellyfish itself does not have a brain. Okay, so what the jellyfish does is it takes in its input from its senses, it processes it and has an immediate response. And it does that without any memory of past events. So there's no brain in there to remember what has happened in the past and to plan for the future. Now, if we think about deep learning in particular, and we think about models that we serve in production that we've trained with deep learning, and we have an example here of computer vision. We have an image that's coming in here. We have a bunch of images. We're going to train the images, so we're going to generate some training data. To do that, we'll probably have to crop the images, resize them, we may augment them, and so on. We'll call that feature engineering. And with those pre-prepared images, we can train models, and we've got a convolutional neural network here that's been trained, and now we want to serve that model in production. So we want to have new input in new test data, images that we've never seen before, and we're going to make predictions on them. Maybe it's going to be classification, segmentation, whatever you want to do in that computer vision problem. So we have our new images in. We're going to have to reuse the same code that we used when we're creating the training images, the same feature engineering code, crop the images to the same size, resize them same size. If we're doing any other alterations to the images, they should be consistent between training and serving. If they're not consistent, we can have skew, and then the predictions we make may not be correct. So we want to make sure that the code is the same, prevent this training serving skew. So we can do that by versioning libraries. And this all works well, and we'll make very good predictions because we have this very rich input. We've got an image with many pixels, and we can make very complex predictions. We can even build self-driving cars potentially on just images. Now, you can do the same with text. Again, deep learning, we can train NLP models with tokenized text, and we want to make sure that the tokenization component is consistent between training and serving so we don't get any skew. And again, we can have very interesting models, but we'll notice that the applications that serve these models are stateless. They don't have any memory. Just like our jellyfish, we just put some input in, it'll give us some complex prediction, complex behavior, but we don't need necessarily to have any historical values of any interaction from previously, or even any contextual information or features about what's happening in the environment at the moment. Now, if we move to many enterprise applications, not NLP or computer vision, where, for example, I want to build a recommender system and somebody's on a website, we have this user identity, maybe we have a session ID identifying the users, and the user's taking some actions, maybe they're typing something into a text box, maybe they're clicking on a button. The data that we have available for that is not enough to really train a useful model. We'll end up with a useless model. And the reason why we'll do that is because we just don't have enough state. We don't have enough context. We don't know the history of the user's interactions with the system. We don't know the context in which this action is being taken place. we just don't have enough good training data to train a good model that's usable. So what we can do is we can add a brain to this model. The brain is the feature store. The feature store can have the historical and contextual features that we'll need to basically to make usable training data. So what we can do on the left here is we can create training data by basically taking features from the feature store related to the user, maybe the product that they're trying to buy. So it might be the history of the user, what they've bought in recent times, features about the product itself, and maybe contextual features about their shopping cart. And we can create training data, train a model, and then when we're serving that model, we can get the same features. We go to the feature store. This time, we're not going to get them as big data frames of features. We're going to get them as individual rows, or what we call feature vectors. And we can build a feature vector with just the user identity and product ID. We can look up those features that are pre-computed and in the feature store. And then that feature vector we can send to the model to make a prediction. So effectively, what we've done is we've taken our stateless model that we had from earlier, the stateless model serving application, and we've added state, we added the feature store. And that gives us history and context, and enables us to build these complex feature vectors. So if we think of the jellyfish example, what we've done is we've given the feature store a brain, which is equivalent to a jellyfish now looking more like an octopus. Octopuses have brains, in case you don't know, and actually very intelligent. They can even recognize humans, and the ones they don't like, they can squirt water at, which is a nice anecdote there. So the feature store is this brain that gives us history and context for predictions, and it fits into the end-to-end ML pipeline. So if we look at this end-to-end ML pipeline here, we can see that we have input data coming in on the left here. We're going to have to create the features. We're going to store and cache these features in the feature store. We'll then create training data from the feature store and train models, validate those models, serve those models, and the serving component will go back to the feature store to retrieve these feature vectors, and then we can monitor models. And again, it can go back to the feature store to get statistics about the training data, for example, to make sure that we can identify things like data drift, because we want to compare the live traffic distribution with the training data set distribution to identify when drift occurs. So let's move on. So who works in these spaces? This is a very long pipeline. We can actually break it up into different roles. So typically data engineers will do the feature engineering parts. They'll take the data from the backend platforms and add it to the feature store. Data scientists also will create these features by creating often derived features from the features that are there, the base features in the feature store. Sometimes they can go to the backend as well if they're talented enough. Data scientists typically train the models and validate them. And then we have ML engineers who are typically responsible for putting these models into production. So serving the models and then monitoring the models and making sure that they're all working as they should. And then finally, there is another role that's often overlooked, which is that you do have to govern this whole end-to-end pipeline. And particularly in Europe, we're introducing regulation for AI. So architects typically are responsible for managing all of the data that flows through the system and all of the actions, and ensures everything is being governed all the way along this pipeline. So when we want to put this pipeline together, what we're going to do is we're going to break up it's no longer an end-to-end pipeline, right? We're not going to have from the raw data immediately getting a model at the end. What we'll have is two pipelines. We're basically going to have something called a feature pipeline, which will take the data from the enterprise. So maybe from Kafka, data warehouses, data lakes, online transaction processing systems, key value stores, file systems. It'll compute features, and it's going to take those features and write them to the feature store. Then from the feature store, we'll have a separate training pipeline, which will do the classic things about selecting features to create training data sets, training models with those trained data sets, validating the models, and then writing out to the model registry. And from the model registry, they can be put into online serving infrastructure, or that you can have batch applications can use them directly. Now, when we talk about MLOps, we talk about automating these different steps. So you would need an orchestration tool to automate these steps, and popular platforms are things like GitHub or GitHub Actions or Jenkins. And the automated steps kick in when events happen, and those events trigger actions. So things like, oh, I pushed some new code, so I'd like to recompute this feature pipeline. Or some new data has arrived in the feature store, let's rerun the training pipeline, or recreate this trained data set and then trigger new training pipeline. Or maybe just once a day, I'm going to retrain a model, or once an hour, or however often you want. So one point just to clear up, which is often people say, well, where do I do my feature engineering in this pipeline? And typically the places you do, if we start in the bottom left here at the raw data, you'll typically do aggregation. So computing, for example, the number of events that have happened in a period of time, like the last hour, last day, last week, validating the data. You're going to do all that before the feature store. And when the data is in the feature store, we often store, for example, categorical variables or numerical features. We'll store those in their non-feature engineered format, non-transform formats. We're not going to one-hot encode the categorical feature. We leave it there as a string so you can see it, or a num. The numerical value will be in its original value so you can see it. And then typically we'll do the one-hot encoding in numerical. For example, if we're doing numerical values, we might normalize them after the feature store. And we need to make sure, again, we have consistent transformations between serving and training. So that's the basic principle. Now, I'm going to talk in more detail about our feature store. Someone asked in chat about Feast. Feast is another open source feature store that's available. There really are two open source feature stores, R1 and Feast. So R1 is a little bit, we have it's end-to-end, and it supports an offline feature store, and it does things like data validation. So the feature store can be used with tools where we want to write data to the feature store. So we can have Python or Spark applications that are going to push these features to the feature store. We're going to take features out to create training data to train models with, and you can do that in any data science platform. And then the feature store will also give these feature vectors to the model serving infrastructure to help them build their feature vectors at runtime to make predictions. And then finally, when we're doing governance of the whole platform, you can have regulatory and compliance frameworks like Informatica and Calibra that can basically interact with our platform to extract metadata to understand how these assets are being used in these pipelines. So I'm going to introduce three abstractions that we have in our platform. The first one is called a feature group. So we don't compute individual features. We typically compute a group of features, because when you go to a backend platform, you go to a table, you go to a data lake, you typically read up a bunch of data at one time, and then you write into the feature store as a data frame, or what we call a feature group. So a feature group is basically got to have a primary key and a bunch of features in it. Simple as that. So it's a table or a data frame. A training data set is a representation of typically the set of features I'm going to use to train a model. So the features in the feature groups are reusable. You can reuse them across many different models. So when you want to train a model, what you basically do is you say, I'd like to use these features from these different feature groups and join them together. And we're going to join them on a primary key. The system is, there is a query planner which will find the largest overlapping set of primary keys between the feature groups, but you can override it and specify it explicitly. But basically, you're going to say, these are the features I want to have. And one of these features is a label for the trained data set. So then this trained data set, you can get as a pandas data frame, but typically you would materialize it to disk. So when you store it in disk, you might store it in TF record file format or NumPy or CSV. And when you store it to disk, we'll also compute statistics over it. And those statistics can be used for data drift when we're monitoring that model in production. Because this training data set typically will represent a single model. You'll have this training data set, you'll have the model that you used to train it with, and then when we're monitoring that model, we can go back to the trained data set and say, well, give me the statistics over all the features, and I can check the live traffic to see if it's the same as the training feature values were. And the last abstraction I'll introduce is the feature vector. So when you're serving a model online, so real time, and we're going to look up individual rows of features, so we call them feature vectors, we typically, the application will have the ID. So it might have the user ID, and it'll say, I have the user ID, but I don't know the history of the user, like how many times they've been on the website in the last day, how many items they've bought in the last hour, the last week, last month. You know, are they a good customer? Are they a bad customer? Whatever. So all of these features we look up with the IDs. And obviously we don't have the label. So we're going to try and predict the label, and we'll build this feature vector in the serving infrastructure. So if we put these things together, what we have then is we have our raw data gets turned into these feature groups. And we have some code to do that. I'll show an example in a minute. And then from the features, we build training data sets. And with trained data sets, we train models. That's it. So let's go into this in a little bit more detail. So the first point is that for the feature groups, these are mutable. They get changed. You're going to write them. You're going to keep updating them. You can have different versions of the schemas of them. You can even have data versioning. So as you write to them, we store commits for every write. And then some of these feature groups will be derived. They're going to be computed from other feature groups, and some of them will be computed from data outside of the platform. Training data sets are created from the feature groups. So we can see that there's this dependency graph between the feature groups, the training data sets, and the models. And any changes in the upstream item, so a change in this particular feature group, might cause this feature group to be recomputed, and then this training data set to be recomputed, and the model to be retrained. So how we break this up, we have the feature pipeline to create the feature groups. So any base feature groups or derived feature groups will be computed in feature pipelines, and then training pipelines to take the features to create training data sets, and then with the training data sets, we'll train a model. How do you do this technically? Well, you can use any of the frameworks I mentioned earlier, GitHub Actions or Jenkins. We support Airflow on our platform. So often you would use Airflow to run feature engineering jobs in PySpark, Spark, Python. And for training, you can even have Jupyter notebooks in our platform. You can have a notebook to create your train data set, a notebook to train your model, and even a notebook then to validate your model in different slices of the data, because you want to make sure there's no bias in that model that you've trained. But it doesn't have to be notebooks. Of course, it can be just simple Python programs. It's your choice. Now, I'm going to go through then these different parts. So firstly, how do we get the feature pipeline? How do we get the features into the feature store? So I have said that we have to write some code to compute the features to get it in, but you may have some code already in a table. Maybe you've got a Delta Lake table or a Snowflake table, and you're computing features in SQL. That's quite common. So those kind of tables that already have ready-made features, you can just import into the feature store. So you're not copying the data in, you're mounting it as an external table. But otherwise, if you want to be able to store these history of the updates of the feature store, the commits, well, then you need to write to the feature store. So what we do is you have a program in Spark or in Python. So it could be PySpark, it could be Scala Spark, or it could be Python. And they basically create a data frame and write to the feature store. Every time they write, we're going to get an update to the feature group, because the feature groups are mutable, as I mentioned already. And from an MLOps perspective, what this kind of looks like, and this looks a little bit more complex, we can see that we have number one, we have new data that we want to update the feature group with, and it can come from different sources. We then have some code that's going to take this new data, and it's going to make an atomic update to this feature group. So we're using a framework called Hoodie by default to make these upserts or up changes to the feature groups. And this will be typically a Spark or a Pandas program, Python Pandas data frame that we're going to write to the feature store. And you can use any sort of data ops CI/CD platform for this feature pipeline. There's nothing special about it. It's nothing really different from a classic kind of CI/CD pipeline. So what does the code look like for this? Well, it's very simple. We have a data frame. We read it up from some location. We do some feature engineering. We create a feature group, and we're going to make the feature group available for both serving and for training. So online enabled is true. We have a primary key for it. It's a multi-part primary key here, and we have a schema version. And then finally, we save the data frame to that feature group. That's it. That's how we create a feature group. And when we want to make an update to a feature group, we can just get a new data frame, the upsert data frame with the new data we want to add. We get a reference to the feature group, and then we insert this data frame to the feature group. So as I mentioned already, because we store the commit history for the feature group, every update we make gets a new commit, and we can go back in time and say, hey, I want to see the state of the feature group as of this point in time, or I'd like to see the changes in a given interval. We can do that as well. And if we update the schema, we can have a whole new version, a whole new schema for the feature group, and that's effectively like a separate table. And it's very good for being able to write pipelines that just keep running, because if someone wants to make changes, they can create a new version and do all their changes on the new version without affecting production code on the old version. So when we write feature to these feature groups, we'd like to be able to validate the data, and we have some support for that. So we have these things called expectations. and you can see that it's based on a framework called DQ. You can say, oh, the maximum value and the minimum value for this feature should be within this range, and you'll get an alert if it's outside of that range. You can also do Spark streaming, so you can take this data and write it continually to the feature store. So you can take data from Kafka in this example here, and we're building it up into a data frame. So Spark streaming has data frames, and then we insert this data frame into the stream, which is basically going to compute the features and then write them out to the feature store. It's going to write them, in this case, typically to the online feature store, so it'll be available for serving within a few seconds. So if we move from the feature pipeline to the training pipeline, what we can see here is that we have our features in the feature store, and the data scientist has some code, but every time we get changes to these feature groups, we might need to create a new training data set. So we can have Airflow to help us do that. And then that can kick off also a training job to train a model. And then we can deploy that model to model serving infrastructure. And then finally, we can monitor the model once it's in the model serving infrastructure. So the APIs we have for creating training data are very simple. We have the feature groups, and we can select all of the features or just a subset of them and join them together. And what we get back then is a data frame, effectively a data frame. You can get a pandas data frame from this object, or you can save this to a file system. So I can save this data frame to this TD object. This is the training data set. And in this case, I want TF record. So if I want to change from TF record to NumPy or to CSV, well, I just change this to CSV, rerun the code, and I'll get my training data in CSV file format instead of TensorFlow record file format. Now we can do a little bit more with the training data sets than this. We can also say, I'd like to have it in a bucket in S3 or in a container in Azure Data Lake. I can say also that I'd like to create 3 splits of the data. So 70% training, 20% test, and 10% validation data. And that's going to be a random split of the data. We only currently support random splits. And other things we can do is we can also add transformations to the features. So I might say, well, this feature I want to one-hot encode. So I'd like to one-hot encode the date feature, and I'd like to normalize the precipitation feature. So you can do that, and when this trained data set is created, we'll now have the one-hot encoded data. The other alternative is to use pre-processing pipelines from scikit-learn or TensorFlow or PyTorch, and then you can save those pipelines and then reload them in your serving infrastructure to apply the same transformations consistently there. The next stage in your pipeline will be to train the models, and that's standard TensorFlow, PyTorch, scikit-learn code. And then finally, you want to analyze your models. So our platform, we have a tool called the What If tool developed by Google, which is a very nice way of slicing and dicing your data. It's notebook-based. So you can basically run your notebooks to get visualizations of the performance of your model against different slices of the data. And then when you want to serve a model, you need a framework for model serving. So we support Kubeflow model serving, which is called KF serving. And Kubeflow model serving has very sophisticated support for lots of features. You can have things like canaries, you can load balance, you can create many replicas of your models to scale out if you have a lot of traffic. You have an explainer component, and you can have this transformer component. And then finally, the model itself is a predictor component. So when you have a feature store, typically the transformer component is a Python program, and this goes to the feature store. This is our feature store here to retrieve the features. So you might have things like the IDs coming in the prediction request, and then we go to the feature store to build up the feature vector, and then that gets sent on to the predictor with the full feature vector. Now, after the feature store, after prediction is made, we support logging of these prediction requests to Kafka. So that's this up here. And from Kafka, we can then monitor the models in production using Spark streaming, for example, to detect things like data drift and outliers. And we can write these results back to the feature store so that you can analyze them. So what the code looks like for that, and this is the Python API, there's also a Scala Java API as well as a SQL API. But what you basically do is we get back the training data set which the model refers to. So that particular object, this TD object, it represents a set of features that were used when we trained the model. So what we can do is we can say, hey, for this particular training data set, there was only one primary key across all the feature groups called location ID. So all I need to do is pass this dict with that particular primary key, and I'll get back the full feature vector completely ordered correctly. So the feature store is responsible for ordering that the features, because you're getting it back to the Python array. And if you get it back to the Python array and you're sending it as a NumPy array to a scikit-learn model or a PyTorch model, well, you need to make sure your features are correctly ordered. Because in training you have a certain order, then it should be the same order when you're serving. So that's basically it. I mean, I've kind of gone through it relatively quickly, all of the steps. But this one slide summarizes it all. This is kind of like, a very large, very complex diagram. But you can see that what we started with our raw data up here, we have some feature engineering to get features in the feature store. And this is where we're breaking the monolithic end-to-end machine learning pipeline. There is no one pipeline from raw data to models. The feature store is the landing point for your data. And from the feature store, we can look for events such as new data arriving, or maybe new training code being created. And we can then run a model training pipeline. The model training pipeline will ultimately create the trained data sets, train the models, validate the models against different sizes of the data, and output a model in a model registry. And from there, you can deploy that model to model serving infrastructure, and that model needs to be monitored. And supporting all of this, you need a lot of infrastructure. So you need the feature store, but you also need some sort of a meta server. And in our case, we have a meta server called RonDB, which is also actually our online feature store. And we synchronize the metadata also to Elasticsearch to allow you to do free text search over a lot of these artifacts and metadata. We have things like experiments with TensorBoard, and then you have tags for the models and the trained data sets and the features. And then you have jobs for monitoring these models. So that's basically it. I have a couple of minutes. I haven't had a chance to look at any questions, but the platform is open source, so you can go to GitHub. This is the reference for it, and you can feel free to start if you like it. It's a managed platform that's available on AWS and Azure at Hopsworks.ai. You get $4,000 of free credits if you want to try it out. And we're on Twitter, of course, and you can reach us. There's an email address for one of my colleagues there, Alina, if you want to reach out to us. And there's a community website behind it. So that's basically it for the presentation. And I think there's a couple of questions here. I don't know if you want me to just go ahead and answer them, Juan, or do you have anything you want to say?
Thank you very much. Thank you, Jim, for such an interesting presentation. We have a number of questions coming in. So you can also see them, right? I can read them. Yes. So
I can go through.
One question from Rene. Why do you not draw a line between feature store and model serving? I think that's a question that came at the very beginning. I saw you had that line at the end, right?
There is a line between model serving and, I mean, the model serving infrastructure. Actually, applications can also retrieve features and build the feature vectors and send them to model serving infrastructure. It doesn't have to be the model serving infrastructure as well. So I can get these. A question from Daniel Wirtz. What's the concept about joinable primary keys across feature stores? Well, if you want to reuse, I have a blog post on this, Daniel. If you want to reuse features, and that's a good thing, you want to reuse features across different models, because if you don't, every time you create a model, you need to write a new pipeline, a new feature pipeline, and you don't want to do that, right? Because that maintaining those is quite a high overhead job. So if you're going to reuse features, you have to join. Join is the basic concept. Reuse means join. So to do a join, you need to have some sort of common ID. So if I have a user and I have features about that user, and then I have the user makes purchases, so I have the user ID in the purchases and I have the user ID describing the profile of the user, I can join those together. Okay, so you mentioned keeping the categorical features as is. Have you seen recommended staging store? Like Snowflake as a first stage. So we do offer, you can have Snowflake as feature tables in Snowflake and just mount them in as feature groups in our platform. That's fine. What is the issue just maintaining a pipeline pushing these features to Bigtable? Well, again, of course, you can, like I said, you can have any external, in our platform anyway, you can have any external data store and just mount them as feature groups. And then the good thing is that we can then take data, features coming from different platforms, and have a single central warehouse. That's what the feature store is, where all of these features can be represented. Now, if all you have is Bigtable and you know of anything else, you can, of course, use Bigtable. The problem is that you can't use Bigtable for for model serving, for retrieving features at low latency. Well, you can. I mean, Bigtable is, it depends. Bigtable is about 10 millisecond latency. If that might be acceptable to you, so then you can go ahead and use it. But Bigtable is not necessarily designed for, for the historical features. Typically, people put them in BigQuery, or BigQuery in that case, if you're on Google. Okay, so then referring from Bigtable at the time instead of any product or Feast. Yeah, well, Feast doesn't build on Bigtable anymore. That's kind of the original Feast. It's changed a lot. So Feast has moved towards us, really. They've kind of embraced the data frame concept. They've used Spark as their join engine. One of the differences, we write directly to the feature store with Spark. So they don't. They have to write to disk, and then they have this thing called ingestion. So it's kind of a write amplification as well. So difference between online and offline feature groups. So, well, they're stored in different databases. One is stored in hoodie tables in S3 or on Object Store. And then the online feature groups are the ones stored in a low latency database, in our case called RonDB. So another one, are there stages for published features? Yeah, I mean, in our case, we can have different feature stores. You can have a production one, you can have a staging one, and you can have a development one, and you can move them between those. Is there a comment on data governance? So what we typically do is data governance is really about how you can use features. So if access control is one thing, so we have in our projects, we have this notion of readers and writers, but you also have the notion of when am I allowed to use a feature? So is this feature for representing users in Europe and is there PII data there? Well, then you need to think about that. I think, Juan, you can interrupt me if we're out of time, because I know we had there's 30 minutes.
Oh, no, that's okay. Maybe just a quick reminder that we have the following number of sessions starting at 11:40. However, we can keep going to answer the questions that are already in the chat. And people, if people are joining the other sessions, just please feel free to move on. But we can keep going with the questions.
I'll do 2 more minutes because there's 4 more questions. So what's the latency from this feature store features? For individual features, about half a millisecond in our case for RonDB. We did some experiments with Spotify where we were retrieving 200 features, and the P99 latency on that was about, so in one request, we retrieved 200 rows, I should say, batches of features, and it was about 1 kilobyte per row, and the P99 was less, it was 20 milliseconds, something like that, 20 milliseconds. Next question, does the join have to be persisted between feature groups? They're not persisted joins. You do persist training data sets, yes. But you can also keep just the metadata and remove the data. That's possible as well, and reconstruct the training data. We haven't automated that yet, but it will come there. Can I make share the presentation slides? I'll upload them to SlideShare after this. Why not use a feature store from Databricks? Well, I mean, you can, but it's not. Ours is the first feature store. It's 2 years old. It's very mature as a product. Databricks is 2 weeks old, I think, and it's not available fully on Azure yet. But feel free to go and compare them and make a decision for yourself. Would feature store be useful for online prediction if all the features needed are already available in addition to primary key at inference time? Well, that's the main use case. Okay, so 2 milliseconds, Vishan, that's actually high. So our database, our in-memory feature store is RonDB. Our online feature store is an in-memory database. So it's Redis style latency. So Redis can give you similar latencies. It's just that Redis is not distributed, and it doesn't have high availability and some other things that our database has. I think we're out of time, Juan. So I had a question. So
thank you very much, Jim. And I'm sure if the attendees have more questions, maybe they can please reach out to you either at the conference, during the conference, or on your website. You have already shared the indications in terms of how to take a look at the website and the platform. So thank you very much, Jim. Thank you to all the attendees. Please feel free to join the other sessions, but before that, go to the polls tab and let us know how you enjoyed this fantastic talk from Jim. Thank you very much.
Thanks, everyone. Thanks all. Have a great day. Have a great conference.